So let me begin this lecture by giving you a bit of notation and background, some background results that we're going to invoke. Um, so the things I'm going to mention here, I'll do this in the context of a lip graph domain, as we discussed earlier. This is the region above a parabolic Lipschitz function. Much of what I'm writing here holds in more generality, for example, in parabolic NTA domains, if you're familiar with those. But for our purposes, the way I stated it will be good enough. All right. So first thing is that sigma, again, the lip graph domain, the boundary of the lip graph domain is Wiener regular. Okay, and this is a consequence of the Evans and Garayapi parabolic Wiener criterion, or caloric Wiener criterion, going back to 82. So in particular, that means that you could solve the Dirichlet problem with continuous data, and your solution is by integrating against the caloric measure, and your solution is continuous all the way to the boundary. Okay? So this means that, in particular, you can construct Green's function and you can do that as follows, given this solvability with continuous data result that comes from Evans and Garayapi. First of all, define the usual Gaussian, the Gauss-Weierstrass kernel. In other words, the usual fundamental solution for the heat equation in n+1 dimensions, n+1 space-time dimensions, and space dimensions. And then we're going to define auxiliary solutions. Let's say v sub ys of xt. So this is going to be a caloric function in xt, and it's solving the Dirichlet problem for continuous data using this as the data. Okay, so we integrate on sigma. We have w of, say, z minus y tau minus s d omega xt of z tau. And it turns out that one can show, this isn't too hard, I won't do it, but it's not too hard to see, that you get the same thing if instead you solve the adjoint heat equation with xt fixed in the fundamental solution. So x minus z t minus tau, then we have then we integrate against the adjoint. So for me, when I write the tilde over omega, this is the adjoint caloric measure, okay, which is, I'll call this v tilde sub xt of ys. It's not too hard to see that these turn out to be the same thing. And then you define the Green function as g of xt ys. You can either set it to be the Gaussian, the fundamental solution, minus vys of xt. But since that's the same as this is also the Gaussian minus v tilde xt of ys. So notice that what's happening here is that, again, you're producing a fundamental solution for the heat equation, which, notice here, in the xt variables for ys fixed in the interior, is going to vanish at the boundary. And similar to this one, for xt fixed is going to vanish at the boundary as a function of y and s. All right, and so notice that it's going to be a caloric function, a solution in the xt variables, and an adjoint solution, adjoint caloric in the ys variables. Okay? All right, so throughout these lectures, I'm going to define a constant m naught. It's going to be defined to be 1 plus the parabolic lip norm of A. So the lip norm, remember, A satisfies A of xt minus A of ys as less than or equal to some constant times the parabolic distance from xt to ys. And the best constant, this is, of course, the best constant that you get in this estimate. Okay? All right. And then I'm going to define a parabolic cube in Rn. I'll denote it by q sub r of xt. So this is going to be the set of y and s in Rn such that these are the components of x. X is, in this case, an n minus one dimensional vector. The xi's are the components. All right, so we have xi minus yi in absolute value less than r, and then t minus s less than r squared. Okay? And we're going to define also a parabolic cube in Rn plus 1. For technical reasons, we're going to elongate it vertically. We're going to write this as, I'm going to set IR at a point x naught xt to be x naught minus this constant, I'll say a word about that in a second, times r up to x naught plus the same constant. Cross with qr in the other n variables. It should be capital R. Okay, so don't be put off by this constant here. I've just elongated things vertically, right? I'm thinking of time as running horizontally. So I'm thinking of my graph sigma is going like this. Okay, so I'm elongating things vertically. The domain is going to be the set where x naught is bigger than a of xt. Okay, and the reason I'm elongating it vertically is that remember m naught is basically, well, it's 1 plus the Lipschitz norm, and this just means that I have set the ceiling high enough that the graph, well, I've drawn the graph pretty flat here, but the graph could climb a bit. I just want to make sure it never escapes and stays well away from the ceiling. Okay, so it doesn't go at the top of my box. Okay, that's all I'm doing. All right, it just gives me a little room. Okay, and some other notation. Maybe I'll put that here. And I hope this doesn't get too illegible on the blackboard. I'm sorry. I'm going to use capital X to denote x naught x. So lowercase x will be a spatial variable in n minus 1 dimensions. Capital X will be the spatial variable in n dimensions. And then sometimes I'll write this with a double bar on top and bottom. This will be the full space-time point. Okay, and I hope this doesn't get too illegible. The same thing with y and z. Okay, all right. Okay, So as long as I've got this picture on the board, so this is my IR. I could consider the double. I've kind of run myself out of room here. I2R. And then I'm going to define time forwards and backwards corkscrew points. Okay, so what are these? There's going to be a point here, the time forward point, which I'll denote as a script AR with a plus to denote time forward of x naught xt, where x naught xt is the center here. Okay, and then there's another one, AR minus is this guy back here. If the center is understood, I'll just write it like this. Okay, so in other words, AR, to be precise, AR plus minus of x naught xt is going to be, I'm lifting it up inside. So let's say x naught plus 2 times m naught r. This x variable remains the same. And then I move forward in time by like t plus, well, either forward or backward in time, t plus or minus r squared. Sorry, 2r squared. Okay? So it's going to be outside of this box, but inside of the doubled box. Okay? Corkscrew point, this is a terminology that goes back to Jerison and Koenig and their work on NTA domains. It just means a point that at a given scale and with a given center, it has a distance to the boundary that's comparable to this point. In other words, it's a non-tangential point, right? It's within it lies in a cone approaching the boundary here, okay? For us, it's a parabolic cone, all right? Okay, so, one more bit of notation. Sometimes I will write a sub delta plus or minus to mean this. When delta is delta r with this center. In other words, it's the surface cube IR intersected with the boundary. Yeah, the domain is up here above. Yeah, I'll always take the domain to be above. Yeah, that makes life easier. Okay. Oh, yeah, sorry. Delta R is the surface cube. Delta R is IR intersected with sigma. I'm sorry, I should have written it. Let me finish with this and then. Okay. Yeah, so this means This just means IR of x naught xt intersect with sigma. So this would be delta right here. Okay, so important for us is going to be the parabolic Karnak inequality. And the thing about that is that necessarily there's a time lag. So what does the Karnak inequality do in the parabolic setting? So here's the situation. We're going to have a point xt. All right. And think of a parabola. Remember, for me, the time axis goes this way. A parabola opening to the right with vertex at xt. And now think of another point, ys, that lies inside of the parabola. Okay? In such a way that, for me, the parabolic distance from xt to ys is less than, say, the minimum of, say, less than half the minimum of the distance from either xt or ys to sigma. So delta of a point xt just means the distance from xt to sigma. Okay? So this is an interior point. We're away from the boundary. All right? Okay, so then in this case, all right, in this case, then we have that u of xt is less than or equal to some, with some uniform implicit constant, the value of u at ys, where u is a non-negative solution. Remember, capital H for me is the heat operator. Okay? And necessarily it has to go this way because you could think that, oh, when I say uniform constant, the implicit constant depends on dimension and the aperture of the parabola, this parabolic cone. Right? So if it's a flatter parabola, right, that means ys would be allowed to be back here, then the constant is going to get larger. Okay? All right? But if you fix a parabolic cone, then, or fix the aperture, then this is a uniform constant. All right? Notice that it has to be this direction only, because imagine that, right, at some time bigger than t, right, say t prime. So suppose that up to here, your solution is identically 0. Okay? So u of xt is going to be 0. And then beyond t equals t prime, some heat is going to be applied to the lateral boundary. So then from that point onward, the solution is going to actually be strictly positive inside beyond that time. So this one could be 0 and this one could be positive, and there's no way you can reverse this inequality. Okay? All right. Oh, no, throughout in the domain. Or really what we could say is that, all right, what we could say is that these points both lie in some parabolic box IR such that the double of the box, such that you have a solution in the double of the box and it's non-negative in the double of the box. That's really what we're saying. Yeah. So, yeah, thanks. Okay? So on the other hand, it would be super convenient if one had a Harnack inequality that acted like an elliptic one, where you had just equivalence here instead of in a one-sided, all right, instead of a one-sided inequality. Of course, as we've just observed, that can't work in general, but sometimes with more hypotheses, we can get a backward Harnack inequality. Which I'll abbreviate as BH. Okay? So there's a sort of prototypical result that I'm going to quote off the shelf from a paper of Fabes, Garofalo, and Salsa, dating back to '84. This is in the context of a lip 1/1/2 domain, meaning that, again, locally the domain is given as the region above a lip 1/1/2 graph. Okay. So it says the following. If h of u equals 0 in some portion of the domain, say omega intersects t bigger than some fixed time t naught, and u restricted to the lateral boundary is 0, okay? So we're going to avoid this problem of applying some heat and making this guy get a lot hotter than this one, all right? So u restricted to sigma is going to be 0 on sigma intersects, again, t bigger than t naught. And we're going to further suppose that, well, we want to stay away from, we want to be forward of this time at the right scale. We're going to also suppose that t is going to be bigger than or equal to, let's say, t naught plus 3 times r squared. That just moves us forward of this time, okay, at the scale that we're going to be working at. And then what we have, I didn't use my board well. So the statement of this result is going to extend over here. I don't want to erase that yet. Okay, and then the conclusion is, I don't want to erase this yet because I want you to still be able to see the time forward and time backwards corkscrew points. Then what we have is that, oh, I should have added that u is non-negative. Well, this gives the board a chance to dry. Of course, it needs to be a non-negative solution. Okay. Then, in fact, we have that u of the time forward point is less than or equal to, with implicit constants depending only on n, and the lip 1/1/2 constant m naught, times the time backward point. I guess I'm using capital R. Okay? So it reverses the direction of the usual Harnack inequality. Okay? And once again, this vanishing on the lateral boundary is something that you have to have. Okay? Okay? Sometimes you can weaken that though, and we're going to see this. With extra hypotheses. Okay? All right, this is taken from something in the book of Caffarelli and Salsa, and I'll actually show you this. All right, eventually. Okay? All right, I should finish erasing this board. All right. So then, I'm going to continue here with various fundamental facts that we're going to invoke off the shelf. There's the parabolic version of what have come to be known as CFMS estimates. CFMS stands for Caffarelli, Fabes, Mortala, and Salsa. These are estimates proved by these guys in the elliptic case, but they have parabolic analogs, which which relate the grain function and in the elliptic case, the elliptic or harmonic measure to the green function. There's a parabolic analog of that, relating the green function to the caloric measure. Okay? And the version that we're going to quote here is, again, these same guys I mentioned before, Fabes, Garofalo, and Salsa, FGS from here on, again, in this paper in 84. And what it says is the following, that if T is bigger than or equal to S plus 3R squared, so again, we just need to move forward a bit. And let's say I use this notation that X with a double bar on the top and bottom is X naught XT. Then and this is the CFMS estimate, the green function at X with AR plus here of Y. Here Y is with the double bars is what you expect it is. It's Y naught Y and S. Okay, we're at scale R. So we divide by that scale. This is going to be less than or equal to the caloric measure with pole at X of the surface ball at scale R centered at the point Y. I should have mentioned this point Y is going to be on sigma. Okay? All right, so this is the the time forward corkscrew point relative to that point on the boundary. X, of course, is inside. And then we divide it by the sigma measure of the same ball. So this is, we're taking an average of the caloric measure, average with respect to sigma. Okay? And then, in turn, this is less than or equal to the green function once again, but with pull at AR minus of Y. Okay? All right. So then, let us notice here, what's happened is that initially here you have the time forward point, here the time backwards point. But remember, this second variable is the adjoint variable. So in the adjoint variable, things of course go in the opposite direction to what they do for the in the caloric case. So here, as you move backward in time, you get bigger. As you move forward in time, you get smaller. Okay. Except what? The green function vanishes on the boundary. Okay. In either variable, either the direct variable or the adjoint variable. Okay. Either an X or Y. Okay. So hence we can apply the adjoint caloric version of BH, the backwards Harnack. Okay? Which means we can put either AR minus on the left-hand side or AR plus on the right-hand side. Okay? So we can have both with plus or both with minus. Which means then, of course, that we have equivalence. They're all equivalent. All right? And as a consequence, we get doubling. We just combine that estimate where everything is actually equivalent and it's not a string of inequalities. We combine that with the usual Harnack, okay? And we get doubling for omega, okay? And again, this is due to Fabe's Garofalo and Salsa in 84. Okay, so doubling just says that this is doubling. Omega with pole at x with a double bar of delta 2r is less than or equal to uniform constants times the caloric measure with the same pole of the surface cube at scale r. Okay? And this is when here x is, as usual, x naught x. Yes? Ah. Oh, that's weird. Okay. So here x is, as usual, x naught xt, and that we just need that t should be, say, forward of t delta r by something on the order of this scale here that we're working at. Here, t of delta r means the time coordinate of the center of this guy. Okay. All right. By the way, these results, the backward Harnack inequality, and the consequent doubling of caloric measure, this is true not just for the heat equation, it's true for general variable coefficient divergence form parabolic operators. That's the result of Safonov in the 90s. It was a big deal when he did that. That was an annals paper. It was a really nice thing. Okay. All right. So more basic results we're going to invoke. There's the so-called comparison principle. Some people call it comparison principle. Other people call it the boundary Harnack principle. Boundary Harnack, not to be confused with backward Harnack. That's going to be possibly a source of confusion because this is often written BHP, and I'm using BH to denote backward Harnack. I hope that doesn't confuse too much. Again, in the context we're looking at, this is Fabes, Garofalo, and Salsa from 84. And it says the following thing. Suppose that we have two solutions. U and V, both solutions of the heat equation in, let's say, omega 2r. Oh, and by the way, this is more notation. I'll write omega with the subscript to mean the intersection of this corresponding elongated parabolic cube with omega. Okay? So these are going to be solutions, non-negative solutions. In this subdomain, they're going to vanish continuously on delta 2r, which of course is the intersection of this guy with the boundary. So this is continuous vanishing. All right. Then what we have, the conclusion is that then for all points y in, let's say, omega r over 2, which is defined in the same way, but it's I r over 2 intersected with omega, we have that the ratio is controlled with implicit constants depending only on dimension and m naught by the ratio of u at the time forward point divided by v at the time backwards point. Okay? But notice that in particular, if v satisfies backward Harnack, then we could put a plus here, right? Because they're comparable. In the denominator. Okay, and also then if both u and v satisfy backward Harnack, then of course you can reverse the roles of u and v. All right, so you get this same estimate flipped, which means that you actually have comparability. Okay? if both U and V satisfy backward Harnack, then we get comparability here instead, equivalence, instead of less than or equal to. Okay? And as a corollary of that, so if both, okay, so U and V as above, right, non-negative solutions, et cetera, okay, both satisfying backward Harnack, then the ratio is actually Heller continuous up to the boundary, okay? Okay, then we get that U of y over V of y minus U of z over V of z in absolute value is bounded by, again, with constants depending only on dimension and m naught, the ratio of little r over capital R to some positive exponent alpha times the ratio of U of AR plus divided by V of AR plus. This is capital R, so this is the ambient scale. And this is for all Y and Z in omega little r of, let's say, x naught prime, x prime, t prime, where this point is any, oh gosh, I'm running myself out of room here. Okay, so where the x naught prime, x prime, t prime is in omega, delta r, the surface cube. And little r is less than, say, capital R over 2. So let me conclude by just drawing you a picture of what's going on here. Okay, so this is I2R. Boundary's going through here. This is the center, x naught xt. This is IR. And what we're saying is that we have this Hiller continuity. As long as we take any center in here in delta R, and we're within, this is I little r, this is the point x naught prime xt, x prime t prime. Okay? So anywhere and here, and this can slide along here. All right. Okay. I think I'm out of time, so I'll stop here for today.